going to review a few different types of functions. We've seen already quadratics, and in general, any even power polynomial function will look sort of U-shaped. Now, there are variations where some will look like a W. You'll have this come down and then go back up and then come down again and then go back up. You have more of a W-looking shape. But in general, it's going to be sort of like a parabola. So here's y equals x squared. The difference between x squared and x to the fourth is between 0 and 1, when you take a number between 0 and 1 to the fourth power, it gets smaller. So what you get is a flatter area here before it rises very quickly. And if I were to add one, do y equals x to the sixth, say, between 0 and 1 it would be flatter even still, and then it would take off. Like so. The higher that power gets, the flatter this looks. Now, this is not perfectly horizontal. If we zoomed in, we would see very, very, very small changes, but from a distance like this, it looks essentially flat. Understand it's not flat. The higher this power gets, the flatter this gets, and then the faster this rises. Flatter this gets, the faster this rises. With odd powers, we've seen y equals x cubed, looks sort of like this. Looks like a half parabola going up, half parabola going down. The same kind of thing. Around between -1 and +1, we get this what looks like a flat area, even though it's not flat, it's just a very, very small changing curve. But because we have very small numbers to a higher power, that's going to involve very small numbers. So it looks flat and then it takes off. Looks flat, takes off that way. And then, again, the higher we make this power, the flatter it looks and the steeper it rises once we get past 1. With radicals, we already know what the plain vanilla radical graph looks like. What happens if we put an odd power there, like a cube root, for example? Well, now we can involve negative numbers. With square roots, we cannot take the square root of a negative. With odd powers, we can take the square root of negatives. So we'll get sort of this mirror image in a way. It looks like this has been flipped and then flipped again, or simply just rotated down, as if we took this and just rotated it down this way. So now we get a second part of the graph. And with any odd index, we will get a two-part graph. With an even index, square root, fourth root, sixth root, etc., we will only get this part of the graph. Oftentimes there's confusion between radical and logarithmic graphs. And there's a little way you can tell the difference. Radicals have a stop. They only go one direction, especially if it's an even index. If it's an odd index, there's no way we're going to ever mistake this for a logarithmic. A radical has a stopping point. A logarithmic continues to negative infinity. But notice, unless we shift it, it will always be on the positive side of the y-axis. What I mean by that is it's always going to be to the right of the y-axis. We cannot take the log of a negative number. We can't do it. It's not defined. But we can get negative results. In other words, I can say I can give an x value, put an x value into a log, and get a negative result. Negative powers are reciprocal. The log is another way to represent an exponent. So if I say something like the log of 1/2, or I say the log of 1/10, I will get a negative result for that. Many log values have negative results. So the way we differentiate between radical and log goes forever in two directions. You can have negative values for y. Radical, unless you shift it, will be positive. You cannot have a square root come out negative. Only way you can get a radical graph down here is if you shift it vertically down. Some review notes here on shifting and stretching, shrinking, all that stuff. Here's a graph of f of x, plain old parabola, and I'm going to manipulate this. I'm not going to sketch graphs for all of these. I'm just going to describe them. We should have enough knowledge at this point where you can visualize my description. I'm going to multiply that by some constant c, 2x squared, for example. That's going to take the graph and it's going to make it steeper. These are going to rise more quickly. 1 over c. Now, by 1 over c, I mean a constant less than 1, say 1/2. Well, it's going to move these a little more to the side, and it's going to rise more slowly. Number out in front of a function affects its rate of increase, or if it's going the other way, rate of decrease. We saw this with trig functions. Something like 2 sine or 3 sine affected the amplitude. Well, with other functions, it affects the rate of increase. I'm going to put a number inside. Now, this primarily pertains to trigonometric functions, sinusoidal functions, when we talked about the period, where we compressed it or stretched it horizontally. I use the example of this affects a pitch. The higher the pitch, the more waves we get in a given space. We increase the frequency, so we see more of them instead of a nice smooth, I'll sketch one here. Instead of a nice smooth curve like this, we get more of a higher, we get more waves. If we had a number like this, 1 over something, say a half or a third, 2/5, whatever it is, it's going to spread out or stretch out our waves, and we get a lower frequency because now we made the period longer. Here we made the period shorter. Again, you primarily see these with trig or any kind of periodic functions. Put a negative out in front of the function. You're going to just reflect it over the x-axis. So let me go back to our function up here. F of x, if I were to say what's negative f of x, it would flip it over the x-axis. So you would see this N shape coming down. It just takes this and flips everything down. This flips everything left to right or right to left. It does not change our parabola. You flip a parabola across the y-axis and it looks exactly the same. So I need a different function for this. Here's my, I will say f of x is, I'll use a square root. Here's f of negative x. If it was possible to do that, that's what it would look like. Flipped it across the y-axis. Here we have a shift C units to the right. Here we have a shift C units to the left. So using our parabola example, shifted it right, shifted it left. Shift up and shift down. All the different ways we can manipulate functions by shifting, compressing, stretching, changing the steepness, rate of increase or decrease. Another little bit of quick review. We can add and do other things to functions. So here I have notation for two functions being added together, two functions being subtracted, multiplied, divided. Again, notice with division, whatever function is in the denominator, it cannot equal 0 in order for it to be defined. This is not composition of functions. And composition is something that was done on a previous video that you can review. Make sure you know the difference between these and compositions. These what you see on the screen here are not compositions. They are merely functions being added, subtracted, multiplied, divided together. Let's just do a quick little few examples here. I'm going to create two functions. I'll say this is 2x squared minus 1. And this other one I will say is, oh, I don't know, the square root of 3 minus x, whoops, 3 minus x. Okay, and here they are. Here's the first function, here's the second function. 2x squared minus 1 and 3 minus x. And there they are. I'm going to make a third function that is going to be one of these four operations. So down in y3, I'm going to say, I'm going to cheat a little bit. Oops. Push my vars button. Go to y vars function. I want y1 plus vars, y vars function, y2. I want the first function plus the second function. Now again, let me go back, shut this off, and go back here for a moment. So what it's going to do is it's basically going to take this y value plus that y value, this y value plus that y value. When x is 0, it's going to add the two y values. When x is 1, add the two y values. So if I go to my table, at x equals 2, f of x plus g of x will be 8. At x equals 3, it'll be 17. At x equals 4, it's no longer defined. So this function, this new function, is going to have some undefined values. Let's see what happens here when I turn this one on. And I'm going to shut these two off so that I don't clutter the screen. And there it is. And we don't get any values beyond that. And it's exactly what I thought it would be. Let me zoom out a little bit. Zoom out. And there it stops. So it looks like this little hook going on stops here. That's y1 plus y2. That's f of x plus g of x. See what happens when we subtract. Looks pretty similar. Let's go ahead and multiply. I want to zoom in on this area here. Let's see what's going on here. And we get this little loop thing here. And let's divide. Interesting. Let me go back to a standard look. And again, if I change my window, let's make Y max 20. Let's see what happens. Nope. What's my maximum value here? Okay. Let's go. Y is 300 max. See what happens. See if I can find a place there. It cuts off. So there's function arithmetic. One function. You can add, subtract, multiply, divide functions. And you can either do them together. So in other words, I could have taken 2x squared minus 1 plus square root 3 minus x, or I could have calculated each one separately, added the answers together. Subtract the two functions, collect any like terms, if any, or simply subtract, or simply find each function value separately and then subtract the answer. We could do either order. Whoops. Clicking all kinds of wrong buttons here. Finally, just a few other things to review then for this section of material. There's video on function composition. There's one that covers the different function types that you need to be responsible for example, linear, quadratic, and so on. And make sure that you can identify each of those types verbally, visually, algebraically, etc. And it wouldn't be a bad idea to review interval notation also.